I'll try to tell you about this method that we developed for multi-omic integration when I was at Duke doing my postdoc. So this method was developed, as I say, like for multi-omics, but it should be super easy to extend to any really high-dimensional data. It's not there's nothing that we do that biology is specific that makes the method only for this type of data. So your data has a story to tell, and some methods tell like only or show a part of the story or stop it early at the beginning. What I'm saying that because most of the methods that we use in if you're familiar with multi-omics or most of the methods that we develop and use are really good at telling us something about our data, like the most relevant. We normally spend like a lot of money and like a lot of time measuring a lot of genes, a lot of metabolites, a lot of the things, and then we end up applying this super complex method, and then this gene came up, and that's what we published. That's going to be our paper. And that's fantastically fine. So from here, I'll make the point that I'm not trying to say that we've been analyzing our data wrong and we need to change, like not at all. And just trying to highlight that there are other things that we can do after applying our go-to method. We can apply this method or couple these methods with other things that allow us to see other parts of our data, because there's more in the story that this gene or this metabolite that we end up publishing. So what all these methods, or some of these methods that the state of the art for multi-omics integration, what they have in common, like as a bottleneck, or let's say bottleneck, in my opinion, is this super simple thing. So the first talk described that, and yesterday at the workshop, same thing. And it's pretty easy concept, but we really never applied that. So that's the most, or one of the most like basic of reactions in biology, nature, like how enzyme saturates with more substrate, and the reaction rate just plateau, and that's clearly nonlinear shape. Like if this is like one of the basic things, and it's like nonlinear, not to mention like all these gene networks and all these interactions between these features. So we can really not expect pretty much anything in biology to be a linear, like few things are really linear associations. What's the problem? That when we do that and we use the exact same data for this super simple example, and then we do a simple person correlation, and this is pretty clear here, but in other cases maybe a little less clear, and especially if we have a lot of samples, the p-value is going to be really low, and 0.7 is pretty good. So we're gonna talking to ourselves like okay, I'm happy with that, I'm happy with this, but this is not really what's going on. We can go for it and publish that, and we're going to be really close to what's going on, but it's not exactly what it is. So most of these methods for multi-omic integration, MOFA and friends, and like big fan, great methods, but they base the method in a linear, like whatever principle, and then they go ahead with the rest of the algorithm, right? And that could be like not dangerous. It's gonna, our gene is gonna come up, and we're gonna see that super strong signal, really easy to interpret, but we're gonna be missing a lot of stories. So another example, again, from the first presentation, I'm gonna use the Swiss roll. Of course, that's not the biological omics data set, but it's a 3D example that works really well to explain these. So we normally don't know this. This is the real shape of the data. That's how, but we never know that. We want methods that can plot these in a 2 space or an interpretable space, maybe 3D or 2D space, that allow us to capture as much information as we can from these data. Okay, that's 3D, but again, like omics, thousands of genes, whatever, and we don't know the data. So if we wanted to plot these in 2D, we would want to do something like this. We want to unroll the Swiss roll, and that would be like the perfect unrolling of it. So in 2 dimensions, we have like the purple is in the other side of the yellow, and then the yellows are like was that far from each other. So, but what happened when we apply PCA? PCA just grabs the real structure and puts that in a plane. That's what linear methods do. And again, big fan of PCA, works well for a lot of applications, but this is really dangerous. I plot like PC1 and PC2 and PC1 and PC3 because like the 2 angles that we have. But here we have the purple points really close to the yellow points. So And again, we don't know that. We don't know the real part of like how the data really behaves. So if that's the only information that we have, we're going to be thinking that the purples are really close to the yellows, or in the other example, the yellows are really close to the yellows, which this is not true in the real structure. So we need to be really careful about what we use to represent our data, because our paper is going to be based on this. We're going to plot a beautiful UMAP or PCA, and then we're going to try to explain it. So we're going to need to be really careful with that. So we wanted to develop something to do this. Like, okay, what's the alternative, right? Like nonlinear methods, of course. So the same structure. In biology, I would say that there are, of course, a lot more, but the two most like used methods are, I would say the first one is t-SNE. Great method, using single cell, used for multiple application. What's the problem, in my opinion, that the t-SNE is a little bit computationally less efficient than UMAP. And the problem here is that it's a good method to preserve the local structure of the point. So if you see like this, it's unrolling the Swiss roll in a pretty decent way. But, oh, there we go. It's rolling this in a pretty decent way, but you will still have these two clusters that really are not in here. This is a continuous manifold, and we have these two clusters. So we could be like misinterpreting that a little bit. The alternative to that, I would say that the obvious one is UMAP. And this unrolls the roll really good as well, but it captures the continuity of the roll. So it's again a little bit more efficient than t-SNE, and it's capturing the two things that we're interested in. It's capturing the 3D the local structure, but it's also capturing the global structure and a little bit better than t-SNE. So this is why we decided like, okay, we're gonna use UMAP for our method, and we're gonna base our method in UMAP. But that's a little bit the elephant in the room that nobody talks about really. When we have like UMAP I think it's a great method, but it's a stochastic method, right? So we, again, like a lot of papers, they have like the cool figure, like the UMAP or whatever, but nobody really says that every time that we run a UMAP, we're gonna have a different result. And I think that's quite relevant because it's not gonna vary a lot. Of course, it depends on the data. It's not gonna vary a lot, but it's gonna change. And then we're gonna do cluster in this two-dimensional space that we know it's gonna be different every time. And then we're gonna trust these clusters, and then we're gonna, again, do interpretation for our paper based on these 2D space. So how, as you see, like all these runs of the same data, again, the unroll, Swiss roll structure, and they all like super similar, but none of these is the same. So they're different. How we solve that, or try to propose a solution for in our algorithm for that. So what we're gonna do, that's all the runs that we have, or whatever. We can do like multiple runs there, but we're gonna run UMAP normally, I don't know, between 3 to 10 times. We can do more, but whatever, depends on the time that we want to spend doing that. But I think 10 would be perfectly fine in a normal data set. And we're gonna have like 10 different embedding, 10 different two-dimensional spaces. This C shape, they're looking this way, but it could be like UMAP, for example, it could be perfectly looking the other way. It could be like rotated, it can be whatever, all different things. So we're gonna grab all these runs that we did, and then we're gonna select one. That's the one that we're gonna use as a reference. How are we gonna select this one? That's not random. We're gonna use, because we wanna do this as a non-linear, non-biased, associated with any like whatever metadata variable that we have. We want to do this like totally blinded, so data-driven. So from all these runs, we're going to use a silhouette score. That is a metric that we have without any other. We could use other things, but then we need to, like, I don't know, if we have sex, or we have age, or we have whatever in our data set, and we're using this information, we're going to be biasing a little bit what we want. So we're going to use this silhouette score, super agnostic, just evaluating the space. And the best silhouette score from all of our UMAP runs, that's going to be our reference. And then based on this reference, we're going to find the maximum similarity configuration between all these UMAPs that we perform. So essentially, we're going to just align them in the same, like, the most similar, again, configuration that we can put all of them. And when we have all of them aligned, we're going to do the median to come up with the final structure. That's going to preserve the signals, and it's going to hopefully remove the noise. Or I mean, definitely it's going to be better than running UMAP only one time. So that's the rationale here. And then we're going to obtain something like this. Something interesting that oh, don't go away. Well, there we go. So something interesting, I think, is that's if we do one run, see a structure something like this, like multiple runs, but we see something a little bit different when we do all this alignment and we put that together. We see like these two areas here that, come on. No. Oh, sorry, that's annoying. There we go. We see these two areas that what they have in common, like because the stochasticity of UMAP, every time that we run it, UMAP needs to decide when it gets to like, well, first, if we see these two areas correspond to these. Oh, sorry, that's annoying. What's that?
How many more slides do you have?
No, not a lot. That's right. Let me try this again.
Or plug in and plug out. Plug out and plug in. Yeah. Or a different dongle. Yeah.
Okay. Try not to. Okay, so these two areas correspond to these two areas. In the actual structure, these two areas are where the slope is more pronounced. So that caught my attention because when we run multiple UMAPs, because they're stochastic and they have these, whatever, anyway, they need to decide, when they get to this point, UMAP needs to decide, okay, do I prioritize the continuity of the role or I prioritize the 3D structure? What's that? Oh, thank you. So do I prioritize the 3D structure to represent the 3D structure in a good way in the final representation, or I decide to preserve the continuity of the manifold? So when we have all these runs, ones are going to do one thing, ones are going to do the other thing. So when we do individual UMAPs, we don't see that because we only see one decision in time. But when we do this alignment plus median, we can see that UMAP in these areas is where the algorithm is conflicted. So when we see this space, we're not only seeing the representation of the role and like everything, but we're capturing other features in a 2D space that are actually telling us about the real structure of the data. And this in a single cell data set could be, for example, cells transitioning state, or whatever. So we can actually, by doing this in a 2D space, we can represent a lot of features about this space that we don't know. So that's what we do after running UMAP, and then we get to the clustering part. So we have this 2D space, and now you've probably seen this example sometime. But then we have this 2D space, and we want to do clusters. We want to create groups in this space. Most of the algorithms, or the most used method, I think, that would be k-means. The problem with k-means, great algorithm, but it assumes that clusters are like spheres. And really, again, in biology, if you've seen like a single cell plot or something like that, really clusters are not perfect by any means. Yeah, whatever, not intended. But they're not perfect at all. So this is just like simulating different data sets and applying these different algorithms. You see how bad is the clustering the first line. It's just not representing the real clusters at all. It's just dividing the space in different like planes. So that's the problem. I put Louvain the second intentionally because that was not in the original benchmark, but they put it here because this is again, if you're familiar with single cell, This is the algorithm that Siret, the R package for single cell, uses as a default. And I put it here. That's from the Siret documentation, actually. I think this is a terrible clustering. I think that like, this is not real. So it just not. This is a cluster. This is a cluster. This is a cluster, and that's definitely a cluster. But this is not. This is the algorithm forcing these planes and dividing clusters that are not real. So we're really two cells that are pretty much overlapping. We're gonna call one type, and we're gonna call one the other type, which is, again, so coming back here, the most important, and then that's what this algorithm does all over the place. We use this one for our method. We base, was that 5? Thank you. We use this method so that method is based on density. We're gonna use the density of this space to create our cluster, not planes, not assumptions, not anything, just the density of all these dots in our space. And this is the method that we selected. The most, you can see like the circles are perfectly like cluster, and all the clusters look pretty good. But for me, the most important one is this one. When we don't have clusters, we don't have clusters, that's it. And that's okay. We don't force clusters. Like, give me 3 clusters. If we ask a clustering algorithm to give us clusters, the clustering algorithm is gonna give us clusters. And then we're gonna, again, try to interpret that and write a paper based on that. So I think that's more relevant for me. When we have one big cloud of points, that's what it is. And maybe we need to find another algorithm or find another solution, but certainly not divide that in clusters and write a paper about it. And finally, when we have the space and then we have the clusters, we want to make sense of this space. We want to interpret like what this space. So what we're going to do is fit different models, non-linear models, because we have a non-linear space. So we can fit like an XGBoost, or we can do random forest, and then use like SHAP for like pick the most like relevant features, or gene index for random forest. We can actually couple both methods and apply both at the same time and see how it works. But essentially what we're gonna do here is, well, the first thing is batch correction, where batch is the omics or the data set. So we're gonna adjust per data set. Look, see like the dots there, like the intracorrelations in the data set. When we do batch correction, they go away. And then we're gonna compute the most relevant features per data set that we put in. And then the final one, we're gonna do concatenation and put all the features together and do that again. So here we have like G stands for gene, M for metabolite, and we're gonna have like features that associate with the first coordinate with the second coordinate. So we're gonna have like features that associate to like horizontal axis and vertical axis. And here's where we can have all features, just like this is a random example, but they all weight the same. So we don't have like gene or metabolite effect or CPG effect because we corrected by that. So now we have all the features in the same like weighting, I would say. So here's where we can do like enrichments, or we can do like whatever. And we can also like, without doing we can go to a cluster and then grab the signature for that cluster. Like we can do like, we do in single cell, we do average from all the features and grab the ones like more expressed or more abundant or whatever. So we have the signature per cluster. And this was a multi-omics talk, but I've been talking about how we do like all the method and our decisions, but really this is only with one data set all the time. So GAUDI is all the things that I explained together, but with multiple data sets. So the part I've been talking about this, but I've not been talking about that. So what we're gonna do for different data sets, we're gonna apply one UMAP per data set, extract the embeddings, concatenate all these embeddings, and now we're gonna do all the things that I've been saying. Like we're gonna do a final UMAP, multiple UMAPs, we're gonna align these UMAPs, we're gonna put that together, we're gonna do the clustering, but is this like just this simple previous step per data set, we're gonna go to the same space and put them together. So we're gonna create a data set based on all the data sets that we have at the beginning. I will be like, if not, that would be like speaking all different languages. If we try to put that together, like we have different weights, different everything. So we just like create embeddings per data set, and regardless of the features that are coming in, we're gonna end up with the same amount of like components components, put that together and do all the rest. And do I have time actually? Or 1 minute? That's enough. So that's a real example where that's a AML data set. That's 114 kids, AML 3 data sets, 22,000 features, not a lot, but good enough. Like we have the cluster, we apply GAUDI, we apply the, again, independent UMAPs per data set, then we put that together, multiple UMAPs, align all the things. The cluster in yellow, and then we have all the benchmark from all the things in GitHub. So if you want to explore how we like decided all of that, and all the benchmark are in GitHub, but the only relevant here is that we found this cluster, the yellow one, that is really different from all these other clusters, and that was unsupervised, whatever. And then after that, we associate that with survival data that we do have for these kids, and we see that indeed the space that the two most different things in the nonlinear space that we created are in reality the most different things in survival as well. So this space is not just applying the method and finding these like colorful and whatever. It's really associating with real biology. Now we can extract the features and we can do the whole thing. But yeah, that's what I have for today. Thank you.